6.6, expressions containing several radical terms. Actually, a lot of this stuff ends up just being combining like terms in a way. Sometimes the terms do not have the same, well, in the past we would call it the variable, but we can force those to be the same. But instead of variables now, it's the roots. Okay, so sometimes those roots can be simplified, and when they are simplified, the roots will match, and that's how we will determine what the like terms are. Sorry if that didn't make any sense. We'll see some examples. Liking rational expressions, as long as the roots match, you can add when these were variables, we call these coefficients, just the factors on the outside of the roots. Now this is a step not everyone shows, right? Usually we usually show it like this. It's like you got 4 roots of 5 and 3 roots of 5 added together. So how many roots of 5 is that? Well, then you do 4 plus 3, which is 7 roots of 5. And you see it's the same thing that's right here. But these roots have to match. If they didn't match, then you cannot combine them. If they don't match, sometimes they can be simplified so that they do match. So you have to be aware of that as well. If you see that, like maybe you got 4 terms that you're adding and subtracting, sometimes these roots can be simplified so that they do match, and then you can combine them. So that's a good point. If the roots do not match, yeah, we do keep those separated in the problem, kind of like you would in a problem with x's and y's, right? If you have an x separate, then you keep the y separate as well, if you're adding and subtracting. So here's what I'm talking about with sometimes the roots don't match. So if you had like the square root of 125, I'm still using square roots of 5, but add this to 2 times the square root of 5. Well, the square root of 125 simplifies into 1 times the square root of, 5 times the square root of 5. And now you can add that to 2 times the square root of 5, which would then be 7 square roots of 5. So again, this is another example. 2 examples for you. There you go. And again, I didn't really show the 5 plus 2 just because I ran out of space. Whether you show it like this, which pretty much no one does, most students show it like this. Either way is good for showing work, but you should end up with the same answer. I guess I got the same answer on this one as well. That wasn't on purpose. That last thing was talking about, like if you got a square root of 3, 8 square root of 3, plus 8 square root of 5 like this. These can't be, this is simplified, it's done. And I put the 8s there on purpose because some students are like, well, 8 and 8 is 16. That's true, but it's not the square roots. It's the square roots that have to match. I don't care about the numbers on the outside if they match. So the roots have to match like we see here and here. So this example, just emphasizing what we just saw. The square root of 10 cannot be simplified. You're welcome to put that in the calculator. But right here, I'm going to combine my square roots of 10. How many do I have? Well, we had 6. And then we're going to add 5 more, which would make it 11 square roots of 10. Done. And again, if this could be simplified more, then we would. And that would be great. But the square roots of 10 already matched, and the square root of 10 can't be simplified. So there's no need to. Just please don't make this more complicated than it needs to be, because sometimes students are like, well, 11 times 10 is 110, and that's now you've gone out of the boundaries, if you will. We notice the pattern. We start out nice and pretty, but well, that'll change. So right here, okay, so 14 times the square root of 7 plus 4 times the square root of 14. Now, can we make these roots match? Well, 7 is prime, so that's okay. 14 splits up into the square root of 7 times 2, right? Now, the problem with this is that neither of these, 7, we know 7 is prime, but 2 is prime as well. Also, it's not a perfect square, which means that at least this part right here cannot be simplified. And we can't get this to match the square root of 7. Now, you could say, well, can you just do 4 times the square root of 2 times the square root of 7? You could, but then you still got another square root in there, and then the square roots don't match. It's the square root of 14. So as soon as we see that this can't be simplified anymore to match that square root of 7, yeah, we'll just put in D and E. That's part of the instructions there. Does not exist. Really, I would just say it cannot be simplified any further, or cannot be simplified. Either way, D and E is good too. Last thing I'll say about this one is that I was specifically trying to get the 14 to match a 7 because we usually match these downwards. Because if you get a big number, then it usually can be simplified into a smaller number, usually. So the way that this would need to be changed is if you had 4 times the square root of 28, then you could have simplified the square root of 28 into 2 times the square root of 7, and then you could have combined those. But 14 is no good. Ah, there we go. Something to sink our teeth into. So let's start simplifying because that will help us hopefully the most. Yeah, right there, right. I mean, it's pretty horrifying. It's true. Now, some students at this point are like, look, I got my square roots of 3. I can combine those. Feel free to do that if you'd like. I'm going to wait to do that, though. What I'd like to see is these other terms simplified first. Okay, so I'm going to start over here on the left. The 343, can that be simplified? Yes, it can. Again, I'm looking for factor pairs where the square root is the biggest, or one of the factors is a perfect square, right? Now, you can use many, but the one that I'm thinking of is 3 and 121. Let me make sure I did that right. Hold on. 114, yeah, thank you. Well, that doesn't work. Yeah, so I made a mistake there, didn't I? Get used to it. So it's not divisible by 3. 3 plus 4 plus 3 is 10, which is not divisible by 3, so I know it's not divisible by 3. What the crap is it divisible by? It's not divisible by 2. Oh, thank you. That's going to work out very nicely. I should have just used my calculator, but you guys are just as good. So that's going to be the square root of 49 and 7, and the square root of 49 is 7. So now you got 4 times 7 times the square root of 7, which now combined would give us 28 times the square root of 7. So that one didn't work out. Again, would have to think more. You guys had it, though, with the 49 and 7. I assume you had that locked and loaded. You guys were just watching me make a horrible mistake there, but it's okay. We recovered. I feel better about it. All right, now let's go to the 175, right? So the 175, 25 times 7, and 25 is a perfect square. Now you notice that on that last one we had the square root of 7. This one, this one, by the way, I was looking at the square root of 3 because we already had square roots of 3, so I kind of thought it would work, but I just didn't give it much thought, which is unfortunate, but we've recovered. Now this one, again, I would look for 175 to be either divisible by the 7 or the 3. The 7 works. The 3 does not. So from there, then, the square root of 25, I know, gives me 5. Now that's still multiplied by really what's negative 10. And then that would be multiplied by the square root of 7 right there. In fact, the 7 will make it the same color so it's pretty. And then from here, you got negative 10 times 5, which is negative 50 square roots of 7. Now, even at this point, I've got square roots of 7 and square roots of 3 that I could combine, but I've also got the 28, which also can be simplified. So I will. Yeah, thank you. 4 and 7, which when we take this, oh man, push the wrong button. Square roots. The square root of 4 is, should have made the 7 red, huh? Square root of 4 is 2. And then the square root of 7 is still the square root of 7. Now, if you apply the negative out there in front, that's fine. Let's make that negative 2. I'm going to write this whole problem over again, though. Not because I like writing, but just so we can see everything as it is simplified. So we got 28 times the square root of 7, plus 6 times the square root of 3, plus 2 times the square root of 3, minus 50 times the square root of 7, minus 2 times the square root of 7. It didn't really line up, but hopefully that's okay. But now that we have this, we see that we got some square roots of 7 that we can combine, right? Square root of 7, square root of 7, square root of 7. So that's going to tell me how many square roots of 7 that I have now. But that would be 28 minus 50 minus 2. Negative 30? No, negative. Use a calculator, please, because I don't want you to make the same mistake I just did. But negative 34, calculator thing, right? It's not. I don't mind making those mistakes. Hopefully you don't either, just while we're practicing especially. Now that's all the square root of 7s that I have, right? But then we also have these square roots of 3s that I can combine. Square roots of 3, and that appears to be 6 plus 2. I can do that one in my head. Usually I can. But that's it. That's all we need on this one. By the way, the order on this one, so some students are like, I don't want to write the square root of 7 first. All right, yeah, I mean, you get the same answer if you write it as 8 times the square root of 3, and then minus 24 times the square root of 7. Either one of these work, and I don't really care which order you put it in, as long as the 8 is positive and then the 24 is negative. That's the main thing. There is another method. It's calculator method. If you had typed this completely in as it was in the beginning, it would have simplified it to either one of these. I don't know which one, but I'm pretty sure it will simplify this. So multiplying binomials and trinomials, we've seen this before, where, you know, like if you got like terms, but now we're dealing with the square roots, right? You can just add them in. But also, sometimes you'll see these as binomials, which then you can factor out here and then just add the number that you would, most students would distribute, but you can just do 4 plus 3 there, which is 7. Now again, most students don't show this step or this one, right? Like we've been doing, you just do 5 plus 2 is 7 x's, and that's how many x's you would have. Same with this one, right? You do x plus 1s, you got 4 and 3 of them, which is 7 x plus 1s, and then you can distribute if you'd like. Again, that's just a nice way to simplify here instead of distributing here and then simplifying. Doesn't really matter. I mean, you should end with the same answers either way. Let's look at this application with these roots. So like this one, right? So we're taking the square root of 15 times the square root of 15. Now I'm going to show probably more work than you'd do usually on this, but combining these, you'd have the square root of 15 times 15, which is the square root of 225. You could have just shown that as the square root of 15 squared, which of course would have just been 15. Okay, and you can do the square root of 225 in the calculator, which is 15, right? Now that's just from that distribution. Some students don't need any of this work right here. They just show this rainbow and then they know it's 15, and that's fine too, if you feel like you understand it that well. But then I've got to distribute the 15 to the 5. So again, more work, perhaps more work than you'd want to show, which is fine. But the square root of 15 times the square root of 5 is the square root of 75. Now, can that be simplified? Yes, it can. That's 25 times 3. Okay, so I now have the square root of 25 times 3. The square root of 25 is 5. And then I've got the square root of 3. Now, between those, I had minus. So really, I probably should have multiplied this by negative square root of 5. But either way, it's now minus between. And that would be considered simplified. Of course, I suppose you could write this as negative 5 square root of 3 plus 15, but I like to keep this in order, right? The square root of the 15 came from the first multiplication, and then the negative 5 square root of 3 came from the second multiplication. But this is as far as we need to go on this. And that cannot be simplified because here's a square root of 3 term, and here is a constant term. Now we got more distribution, right? But again, is it difficult distribution? I hope not. And so I may be showing more work than you'd want to show on this, and that's okay if you don't show as much work, but you would want to show work on an exam. Right off the bat here, I've got negative 4 times negative 3, which is 12. And that was pretty nice. But then I've got negative 4 times, I'm going to show that times by negative square root of 10x. And that 10x can be simplified. But negative 4 times the negative would make that a positive 4 times the square root of 10x. Okay, now I go to the 3 times the square root of 10x and multiply it by negative 3. So 3 times the square root of 10x times negative 3, which would be negative 9 square roots of 10x's. Now what I just did right there, in both of these parts right here, some students are like, you can't do that because these are not like terms that you can combine. Okay, but you can because it's multiplication, not addition or subtraction. And then finally, we have There's a lot of writing, but 3 times the square root of 10x times that, I'm going to show it as negative square root of 10x. But what we end up with, again, I'm showing more work here, and then I'll come back to it. But I'd have negative 3, and that's from 3 times the negative. But then we got square roots of 10x times 10x. Now, some of you would just say, well, I know that's 10x, and that's fine. Again, I'm showing more work than you'd need to show. That's square root of 3 times 100x squared, which is negative 3 times the square root of 100 times the square root of x squared, which is negative 3 times, really, the square root of 100 is 10, and the square root of x squared is x. So we end up with negative 30x. So that's what I got right here, negative 30x. So all this work, most students may show a little bit of this work. Maybe they skip these 2 steps and they'll show this part right here. Some students, they don't need any of this work, and they just know that you'd have negative 3 times 10, which is negative 30, and then you got the square root of x squared, which is x. Again, that probably takes a little bit more experience than what you guys have right now, but if you have it, feel free to do that. Now, for some of you guys, some students are like, hey, how do you get 3 times negative is negative 3? Another way to look at that is as a negative 1. Again, as a phantom 1, it was there the whole time. So you could just say that 3 times negative 1 is negative 3, if you prefer to see it that way. Now that's pretty good, right? We got 4 terms right here. Are there any like terms that we can combine? There sure is. Specifically with these square root of 10x's. Okay, so how many of those do we got? Well, you got 4 minus 9, which is negative 5 of those square root of 10x's. So I still got my 12 in the front, and then in the tail end there I got negative 30x's, and that's it right there. Now again, if you could simplify this more, you would. Or if it had a denominator that was a square root, maybe you would rationalize that. There isn't, so we're good. So a conjugate, okay? So a conjugate, notice that this arrows go both ways right here. So if you have, it doesn't change the first term. It's just the operation between. So if you have addition, you're going to multiply, or you're going to use the subtraction as the conjugate. So it's only opposite in terms of operation, not signs completely. But what happens here, hopefully you remember this stuff right here. This is kind of like a difference of squares kind of thing. Okay, so A minus B, I'm going to show this even though it may not make a lot of sense, but you could take A minus B and instead show it as the square root of A squared minus the square root of B squared, right? Now the reason I'm doing that is because this then is a difference of squares, and then you'd have the square, remember this, you got the binomials with addition and subtraction, but now it's the square root of A and the square root of B and the square root of A and the square root of B. So as it turns out, if you were to multiply these out, then you essentially get rid of the square roots, which leaves you with A minus B. This is another way, conjugates are another way to rationalize denominators. In the last section, we saw denominators that were just straight multiplication. If we see addition or subtraction in those denominators, we have to use conjugates now to get rid of the square roots. And sometimes, like the first term here, maybe this one's not a square root, but the second one is. Okay, but then you multiply it by its conjugate, and then you get a non-square root, or you rationalize whatever the denominator is that you're looking for. This, of course, like I'm saying, is for rationalizing denominators. It can rationalize numerators as well, but mostly for us, we're just looking for denominators. But the conjugate, taking the same 2 values in your binomial, just switching the sign. Sometimes you'll have subtraction, you'll need to use the addition as its conjugate, which then again creates a difference of square scenario backward, and then you get values without square roots. This denominator here, and for the most part, it's usually beneficial to see this in parentheses so that we don't get values mixed up. But I'm going to have to multiply this 7 minus the square root of 5 by its conjugate. So the conjugate keeps the values the same, 7 and the square root of 5, but now I multiply it by the opposite operation. So where it was subtraction, now I'm going to multiply it by the positive. And again, if I do that to the denominator, I must do it to the numerator as well, which I will get to, but let's focus on that denominator first. Okay, so let's take that denominator, set it aside, and then do that multiplication. So from there, you got 7 times 7, which is 49. I'm going to hopefully kind of go through this kind of fast, but then 7 times the square root of 5 would be positive 7 times the square root of 5. Now this is a negative 1 times the square root of 5 times 7, which is negative 7 times the square root of 5. And we see that difference of squares coming to fruition. But then I got negative 1 square root of 5 times the square root of 5, which I will show probably more work than you'd want, but it's negative square root of 5 times the square root of 5. But you see these two middle terms. 7 square roots of 5 minus 7 square roots of 5 is 0 square roots of 5, which means that really this is just a 0 term. These two end up zeroing out, just like you would with a difference of squares. So I got 49, but then I've got over here, this is square root of 5 times the square root of 5, which is the square root of 25. I skipped some work there. Square root of 25 is 5. Now between that, we had this subtraction there, so it's 49 minus 5, which is 44. So my new denominator actually is just an individual value of 44. So that rationalized that denominator with the conjugate. Okay? Again, all the work between here and here is this down here. And then the rest of it, I can just distribute that. So I got negative 7 times 7, which is negative 49. And then negative 7 times the square root of 5, which is negative 7 square roots of 5. And that right there is all we want in the finished product. This would be considered, well, yeah, sometimes you may look for maybe this constant and then this number being multiplied by the square root can be simplified with the denominator, but I don't see that happening right here. So that's just finished. This denominator came out as an even 44. Sometimes they'll have x's down here, and then you may have x's in your denominator. That's okay as long as there's no square roots. That's what we do not want in denominators. So when rationalizing denominators like this one, all it's saying is that we just don't want that square root of 6 there in the bottom. So we're going to use a conjugate in order to get rid of that square root of 6. So I'm going to take this fraction, I'm going to multiply it by 1, which really just means that I'm going to multiply the numerator and denominator by the same thing. But just like we saw last time, we're going to keep those values the same, 2 and the square root of 6. But the conjugate is where we see we're adding the 2 and the square root of 6. I'm going to multiply it by 2 minus the square root of 6. Now, we talked about this last time as well. It may be helpful to see this stuff in parentheses so that as you work with this stuff, you don't just work with one of the values, because that happens from time to time. A student may not actually put the parentheses here, but then they just distribute this square root of 6 into the parentheses. But it's not just that value. We're distributing all of it, okay? So from here, we're just in a distribution phase, and it doesn't matter if you do the top or the bottom first. We do know, however, that the bottom should end up being 4 minus 6. And that comes from the difference of squares is just in reverse now, because it's addition and subtraction of two binomials that are using the same values. And so you just square the first term, square the second term. Squaring 2 would be 4, and then squaring the square root of 6 would just be 6. Now I'm going to show the work for that, though, just in case you don't remember. So right here I would have 2 times 2, which would be 4. And then I would have 2 times, that'd be negative 1 times the square root of 6. So that'd be negative 2 times the square root of 6. And then I'd have to distribute this square root of 6 as well. So 6 times, square root of 6 times 2 would be positive 2 square roots of 6. And even right there, you can see those two middle terms, the two middle terms we're going to end up with are going to zero out. And then we got the square root of 6. It's a square root of 6 times the negative square root of 6, which I've already put the negative there in the front as a minus sign. But yeah, when you multiply these two together, square root of 6 times the square root of 6 is really the square root of 6 squared, which is just 6. Because a power of 2 and a square root will zero each other out. And then, like I said before, these two values are going to zero each other out. So I end up with just the 4.
It doesn't matter that you had it. So we have 4 minus 2 times
Yeah.
square root of 6.
Yeah, so
Times square root of 6 minus.
So that's how we get this 4 minus 6 there in the denominator. Now the numerator is going to be a whole different story, so I'll have to work there. And I guess I'll just do all the work there in the numerator. So I've got 5 times 2, which is 10. That's easy. 5 times the negative square root of 6 would be negative 5 square roots of 6. Probably need a longer fraction line here. Then I'll distribute the 6. 6 times square root of 6 times 2 would be positive 2 square roots of 6. And then we've already done this before, but it's minus square root of 6 times the square root of 6. I'm going to skip the work on that. Hopefully that's okay, but I get minus 6 right there. So this is what I have, and again, this is just in an effort to rationalize the denominator, which actually we've done, okay, because we've taken away any square roots in the denominator. I know now that in the denominator, 4 minus 6 is just negative 2. All I really need to do at this point is simplify the numerator, and if it can be simplified further after that, then we will, but let's see. So let's take, I'm going to take the constants, 10 and minus 6, or negative 6. 10 minus 6, there would be 4. And then we got square roots of 6, right? So I got square root of 6. I got negative 5 of them, and then positive 2, which would be negative 3 square roots of 6. I don't see that can be simplified. I just know, and I think the assignment accepts this format right here. I did forget to check, but I do remember it showing them to split. So what that means is you split it into 2 separate fractions, which is what the common denominator really tells us right there. So the 2 fractions here, which can use some simplification, but that'd be 4 over negative 2, right? Because we got the common denominator of negative 2. And then you got negative 3 square root of 6 over 2. But then, of course, you can see 4 divided by negative 2 there. That would just be negative 2. And then even the double negative right there would need to be simplified at that point to be a plus. And then it's 3 square root of 6 all over 2. I don't know. I'm not a huge fan of this simplification stuff. I really like just ending it right here. But again, I don't remember the assignment specifically accepting this. We did talk about this last time, but reducing an index, what you got to do is they shouldn't have anything beyond like base 4, I suppose, which really is just a base 2. But you need to look for any bases that can be simplified into smaller bases, like 4 can be reduced into base 2 to the power of 2. Right, because this is all exponent stuff, right? So you're looking for anything that can be reduced, something that can be multiplied by itself, right? 27 is 3 to the power of 3. 3 times 3 times 3 is 27. Or, for example, 64 could be 4 to the power of 3, or it could be 2 to the power of 6. It depends on a common exponent that you're trying to get with all of the other exponents that are in the problem. And then, if it's being square rooted, then you can just kind of divide them all by that index value. But they need to come out as common denominator fractions so that as you change those exponents into fractions, that you can, after you've simplified those fractions, you can change them back into their root form. So that may not make a ton of sense. Hopefully the example will clarify that, which we've already done. But if you change the exponents to fractions, you will need to make sure all the exponents have the same denominator, which I just said, okay? So let's see. But on this one, reducing the index, you got the 20th right there. What I need from all these terms, I'm just looking on the inside right here, this stuff, okay, is what I'd like to do is rewrite these, but with exponent multiplication. Okay, now the reason I want that is because if I can find a common factor from these exponents, I can just divide by the 20 there, and then it simplifies. It should simplify evenly. So, for example, I got that x to the power of 8. Let's start with the x's. I know I could write that as x to the power of 2, and then I'd have that to the power of 4. Now, this power of 4 I know is good because it works with 12 and 12 as well. So if I look at the y, which is to the power of 12, I can now write that as y to the power of 3 times 4. Okay, and then the z as well, same idea with the 12 thing. So I know that's 3 times 4 as well. So usually I do focus on the numbers first. Here I did the letters just because I'm trying to emphasize that we want a power of 4. Usually the letters will show this faster than the number will. Okay, but 16 I know is the same as 2 to the power of 2, 4, 8, 16. That's 2 to the power of 4. So I can just write this as 2 to the power of 4. Now these 4s are crucial that they match. Okay, now some people would just do division, by the way, and that's fine. But I can now rewrite this whole expression here as I'll use a different color, but it's the 20th root of that stuff. So this, all this stuff that I have right here is exactly the same as the stuff we started with. It's just written in a different way, that's all. Okay, but what does this mean for us? Well, I'm going to take my bases of 2, and I'm going to show it as x squared, and then y cubed, and z cubed. It's not a great 3. But then we had these all to the power of 4, right? I don't know if this is the best way to show it, but the 4, since it's the 20th root, we're going to divide all the 4s by 20, and you'll see that these fractions will simplify. So maybe it may be beneficial to put this stuff in parentheses here. Okay, so now I've got a 2 simplified. That's going to be the power of 1/5. That's 4 divided by 20 simplified. And then we got an x squared. So I'll put it in parentheses. But again, that simplifies to 1/5. And we expect all these fractions to be the same, the 1/5. And then you got a y to the power of 3. Whoops. And that also, 4 divided by 20 would give us 1/5. And then finally a z to the power of 3, but to the power of 1/5. So see how we had a denominator or a index of 20, but now that I've written it this way, I can now write this as the 5th root. The 5th root of whatever I had left over, right? Because I had the 2, then I had the x, the y, and the z to the power of 2, 3, and 3. And this right here, having reduced the index of the radical completely as far as we could go, that's good. So be careful, because some students would say, I know I can divide this all by 2, so that would have been 4 to the power of 2, x to the power of 4 to the power of 2, y to the power of 6 to the power of 2, z to the power of 6 to the power of 2. That would reduce the index, but it doesn't reduce it completely. So that would reduce it to 10, and then you'd have to again reduce it to 5 if you did that. But this is one way to reduce the index on radical. So multiply and simplify the given functions, assuming variables are greater than 0. Not that we really care about that. We're just going to simplify here. So it says here we're going to take f times g of x. Okay, so that's really just f of x times g of x, which we know f of x is this right here. So we're going to take this and multiply it by g of x, which is this right here. And what the heck, let's put a multiplication between there to make it official. But okay, is that simplified though? Or is that, well, it didn't say to simplify, but that's what we're looking for. We need to multiply these, right? Well, I can't multiply them right now because the indexes are different. If they were the same, I could combine these into one full root and then add or subtract the exponents, but I can't do that right now because the indexes are different. So I'm going to rewrite these. Let's start with the first function, f of x, right, where we had a and b. The a had an exponent of 1, the b has an exponent of 4. So 1 and 4, but we have that root, the 5th root there. So that's going to be 1/5 and 1/5, 4/5. Let's forget my 4 there. Okay, so that does not change the value of the expression. It just changes the format, the look. Same exact function though. But I have to do that with g of x as well. Okay, but g of x had that index of 6 though, right? So we have the two bases, a and b. A has an exponent of 7, b has a phantom 1 exponent. But now these are root 6s. So that's 7/6 and 1/6. All this is being multiplied, right? So we're going to take the common bases. There's only two, a and b. And I'm going to take the exponents of them and then add them together. Why am I adding them? Because we're multiplying everything. So when we multiply the same bases, we add the exponents. So it would have been 1/5 for base A, and then we're going to add the 7/6. And then the B, we had 4/5 exponent, and then a 1/6, which again, we're adding because the bases are being multiplied. Now, you can do this by hand if you'd like. And I'm not doing this really just to save time. I'm doing it because I really would like you to just do it on the calculator. If you want to do it by hand, feel free to do it.
But we'll have to show our work, right?
So in my calculator, I'm using the n over d function as well. So 1/5, I'm doing the a, base a. 1/5 plus 7/6. Enter, I got 41/30. And this means something for us, which we'll get to, but let's put this in, 41/30. And then in the calculator, 4/5 plus 1/6. Enter 29/30 for b. So the good news here right now is that they have common denominators. That's great. Because with that, I can now take our bases, a and b, and since we have denominators of 30 for both, then I can make these both in the root 30th, the 30th root. But for a, we would have 41 of those, and for b, we would have 29.
And this is the format we want for our answers?
Yes. However, and as fun as that was, we're not done. Because there's enough a's here to make a full a that I can yank out of this, right? How many of them do I need? I need 30 of them, right? So instead of showing that as a to the power of 41, and I will show more work here, probably not, hopefully not to your detriment, but we got the 30th root. But I'm going to take the a and split it up into two parts. This is a little bit different than what we've been doing in the past. Not everyone needs to show this type of work right here, but I'm just trying to emphasize what I'm doing, right? So 41, I'm going to split up into 30, and then also another 11 right there, okay? And then I'd have b to the power of 29, nothing I can do with that, right? If I had enough b's, if I had 30 or more b's, then I could yank one out as well. But at this point, I'm going to go back to one of our old root rules, and this would be the 30th root of a to the power of 30. And then we would also have the 30th root of a to the power of 11 and b to the power of 29. And with, well, I think I can, what the heck. Let's take this out just a little bit. But a to the power of 30, it's a to the power of 30, but the 30th root of that, those 30s essentially just become a phantom 1, so I'm just left with that individual a. The rest of it remains. So this is my final simplified answer right there. I'll put the multiplication so we know it's not a to the power of 30. And again, just a lot of students, they just say, well, I can just take 30 out of this one to pull out the a, and that's true because it'd be 30 divided by 30 if you want to look at it that way, right? You could come back here and say, well, this would be up here, that would have been 41 divided by 30. That would have been a to the power of 1 with a remainder of 11. Again, that's just from dividing this with long division, not that I think anyone really wants to do that. That's this a to the power of 1, that's where this comes from. A to the power of 11, that's where this one comes from. There's so many routes you can take in getting to this final solution here. I just took one route, okay? This one's going to work pretty much the same way, and I'm going to start by focusing on this fifth root, the first set there. So we do have the two bases, a and b, and the exponent of a is 1, the exponent of b is 3, so 1 and 3, that's my numerators for these, and then they're both going to have denominators of 5. So I'm just changing the format so I can start to combine the bases. And then also we got the 8th root of a squared and b. So again, we have the two bases, a and b, with exponents of 2 and 1. So a to the power of 2, b to the power of 1. But again, these are over 8 because of the 8th root. Now that I've got that, I can take my two bases, a and b, and I'm going to take my a. I'm going to start with a's. I got the 1/5 and the 2/8. And I know that can be simplified. I really don't care that it can. But I'm adding those two together because we're multiplying these bases together. So if you want to do that by hand, that's fine. But I'm just going to use the calculator. So I got 1/5 plus 2/8. And it says, all right, you got 9/20. Now that may be simplified, and that's okay if it is. But let's see what happens with the b's as well. So with the b's, you got 3/5, and then well, I can do better, 5. 3/5 and 1/8. And again, since we're multiplying the bases, we'll add the exponents. So then I got b to the power, let's see, 3/5 plus 1/8. And I got 29/40. Now the problem here is that when I have done this with the calculator, I did get different denominators for my exponents. So what I'm going to have to do is force those denominators to match. And I'm going to have to use the bigger one. Okay, so I'm going to keep the b to the power of 29/40. What I'm going to do is I'm going to make the a to the power of something 40ths. Now to make that 20/40, it's not hard. You just multiply it by 2. But to scale that fraction, you got to multiply the numerator as well. So in the numerator, 9 times 2 is 18. And now everything is in 40ths. Okay, now why is that important? It's because now I have my a and b, but I'll keep the numerators, so 18 and 29. But my denominators of 40, that's my root. But again, you can only do this. If I had kept it up here as 20 and 40, it would have been two separate roots, but I want this as one root. So I scaled this one up to 40, even though this can be simplified to 9/20. I forced it to be a 40th so that I can make the root in 40ths right there. And that completes that problem. So on this one, I'm going to get it started at least. So it's f of x divided by g of x is really what this is saying. You're going to take f of x, and you're going to divide it by g of x. And so we're going to make this a fraction. We're going to take f of x here. Let's see if I can get this out. And g of x. There we go. Now, the thing about this, especially with division, and it would be the same with multiplication, is since I'm dealing with the same index here, which is not shown, it's an index of 2, square root, is I can actually just take this and make it one full square root. Now, why would I want to do that? That's because in the numerator, I've got 8x to the power of 15, and in the denominator, x to the power of 10, right? See if I can do a better 0. That's not great, but it'll work. So what does this mean? Well, I can't do anything with a, but I can do something with the x's, right? So I got x to the power of, really, I'm going to take x to the power of 15 and then subtract the 10 because we're dividing those bases. And so it ends up being just x to the power of 5. Okay, so again, like I said, I can't do anything with the x, so I got the square root of 8x to the power of 5. All right, now I'm going to show, again, I'm doing more work than you probably need to. Really, I would just type the square root of 8 in the calculator and then see what it gives me, which is 2 times the square root of 2. But here's some work for you, okay? So I'm going to split this up, right? So you got the square root of 8, which really is the square root of 4 times the square root of 2. And I am skipping some work there on purpose because I would really like for you guys to just do this on the calculator. But that would be then 2 times the square root of 2. Kind of an ugly 2. I don't know what happened there. That one's still pretty ugly. All right, and then we look at the square root of x to the power of 5. I'm going to split it up into two parts. You got x squared, and just x, but all this being square rooted. And the square root of anything that's to the power of 2 is just whatever's inside there. So it's x times x, and then the square root of x just stays. And so we end up with 2. You got 2 x's, so we'll make that x squared. And then whatever was left over, you got a 2 and an x. And there you go. Yeah, so I did skip maybe just a little bit of work there. Hopefully for the, yeah, well, I hope for the benefit of everyone. Combine and simplify, fair enough. So this one works exactly the same way that we did the other ones there. So it is, I mean, let's keep it as a fraction for now, even though I'm going to change that later. But we're going to take the bases here, x's and y's. I'm just working in the numerator. I'll come to the denominator. So right now there is the denominator. I'm skipping that because I don't want to worry about it right now. All I want to do is focus on one part at a time. That's going to help me to keep things organized, well, hopefully. So I've got an x to the power of 2, so it is to the power of 2, but it's the 5th root of x to the power of 2, so that's really x to the power of 2/5. And even the y, which is to the power of 6, but again, it's the 5th root. I can do better 6 than that most of the time. It's 6/5. Okay, so this is just the process, like we saw earlier, of taking a root and rewriting it with a rational exponent. It's not the funnest thing to do, but it's something to do. All right, in the denominator, because I just worked in the numerator there. Now the denominator, I've got x to the power of 1, y to the power of 7. So x to the power of 1, y to the power of 7. But this one is the 8th root, right? We have an index of 8, so now it's a x to the power of 1/8 and y to the power of 7/8. Okay. Now I've kind of purposely put some distance between the x's and y bases so that we can work with those separately as well, which is, I like it because it's going to make things, again, it should make things easier to organize. All right. So just with my x's, because, all right, well, now that we got that out of the way, so I'm going to take the two exponents, right? So we take the numerator exponent, which is showing as 2/5, and the denominator exponent, which is 1/8. But this time, since we're dividing, we're going to subtract those, all right? And again, just because I want to keep working with my x's, if you will. Oh, my calculator. Again, I don't expect you guys to do this by hand. Just put it in the calculator, be done with it. So I got 2/5 minus 1/8. Enter, and it says, oh, you got 11/40 of those x's. X to the power of 11/40. We should get the same denominator with the y's. Let's find out, though. Now, the y's, we had exponents of 6/5 and 7/8. But again, since we're dividing the bases, we're going to subtract those exponents. Now, this should give us a new exponent. So, but I'm just doing this in my calculator, 6/5 minus 7/8, enter, and I got 13 for you, so that's nice that we did get the same denominator, because now I'm going to take my bases of x and y. And we're going to keep the numerator exponent, part of the exponent, 11 and 13, x to the power of 11, y to the power of 13. But now with my base, with the denominators of those exponents being 40, I now have the 40th root of those. And yeah, I don't see, remember, if I had more than 40 x's or y's, then I could yank one out, but I don't. This is not enough to yank any of those out. In other words, pretty much if you end up with an improper fraction as your exponent, then you should be able to pull something out, or some things, whatever.